Picture a quiet control room just before dawn. Coffee going cold, screens humming. A survey telescope in Hawaii scans the sky in wide, patient swaths, the way a lighthouse sweeps the sea. Then a tiny streak appears where no streak should be, moving a little too briskly against the background of seemingly fixed stars. In that unremarkable smear of pixels, the universe cleared its throat and said, "Pay attention. Earth is basically a rock that won the cosmic lottery, and today it drew a bonus ball." Good evening, curious minds. Science doesn't need to shout to be fascinating. Sometimes it's best enjoyed the way you'd enjoy a late-night conversation, quietly with a cup of tea and maybe the soft hum of a fan in the background. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing. No pressure, only if you enjoy these calm journeys through the universe. Now, let's begin. Chapter 1, Discovery Day. How we spotted a visitor from the stars. Picture a quiet control room just before dawn. Coffee going cold, screens humming. A survey telescope in Hawaii scans the sky in wide, patient swaths, the way a lighthouse sweeps the sea. Then a tiny streak appears where no streak should be, moving a little too briskly against the background of seemingly fixed stars. In that unremarkable smear of pixels, the universe cleared its throat and said, "Pay attention. Earth is basically a rock that won the cosmic lottery, and today it drew a bonus ball." To understand why that faint streak made astronomers sit up straighter, you have to know how we keep watch. Modern sky surveys are not lone astronomers with notebooks. They are tireless robotic systems that repeat the same photographic dance night after night. The telescopes capture wide fields. The cameras gulp down millions of stars at a time, and software compares tonight's image to last night's, and the night before, and the one before that. If something moved, brightened, or blinked, it gets a flag. Think of it as cosmic difference spotting, like playing the world's largest game of Find the Change, except the stakes include planetary safety and fundamental clues to how the solar system works. The pipeline is a relay race. First, the telescope feeds raw images into a cleaning stage that removes cosmic ray splotches and camera quirks. Next, a detection stage hunts for points of light that shift between frames. Then a linking stage tries to connect those points over time into a track, which is how you tell a real moving object from, say, a passing satellite or a camera burp. Finally, a fast orbit fitter estimates a path. If the early math whispers that the object might be new, the software fires an alert into a global network where professional and amateur observers can follow up. Astronomy is a team sport with a very large field. On this particular Discovery Day, the flags started piling up in a pattern that was not just interesting, but weird in a delicious way. The object was not creeping like a normal asteroid cruising within the family lanes of our solar system. It had the swagger of something inbound from far beyond, a speed that did not care about the sun's usual immigration rules. Most of the rocks we track are on closed loops, politely bound to our star in ellipses that bring them around again. This one traced an open path that says, "I am only visiting." If an ellipse is a racetrack, this was a highway exit ramp from another state, straight through town and back out again without slowing for the scenic overlook. Cue the automated alerts. They are the astronomer's equivalent of a fire alarm, except the goal is not to evacuate. It is to sprint toward the data. Observatories around the world pivoted. Some caught the object in visible light to measure how its brightness changed, which tells you about spin and shape. Others used infrared to sniff for warmth that reveals size more honestly than reflected sunlight alone. A few aimed for high-speed photometry, sampling the light many times a minute to look for flickers that a lumpy, tumbling body would produce. Within hours, a rough picture formed, new, fast, and on a path that did not loop back. In other words, not from here. Why is this a once-in-a-decade kind of twist? Because the sky is big, the objects are small, and time is cruel. Interstellar visitors barrel in, whip around the sun on their open curves, and fade into the deep for good. You do not get a second chance. Catching one requires several lucky alignments, a bright enough object, a geometry that puts it in the right part of the sky, clear weather, and a survey cadence quick enough to notice the movement before it is gone. The survey telescope that rang the bell is designed precisely for this kind of vigilance, scanning large slices of the sky over and over like a security camera that never sleeps and never blinks. Another reason it is rare is that the telltale signature does not pop out in neon letters. Speed alone can mislead. Some local comets get fast when they dive toward the sun. What clinches the case is the shape of the path paired with the inbound velocity far from the sun's pull. The software has to disentangle those clues quickly, hand them to humans, and trigger follow-up observations before the object slides into the glare of dawn or twilight. It is like spotting a rare bird at the edge of a forest trail. You get one clean look before it disappears. There is also a cultural thrill to Discovery Day. Astronomers are trained to be skeptical, but we are also allowed to be excited when the universe throws a curveball. Slack channels, mailing lists, and late-night video calls light up with questions. Is it real? How confident are the early fits? Can we get radar? Who has the right filter set to catch a faint coma if it starts to shed material as it warms? The community becomes a flash mob of focused curiosity, everyone grabbing their piece of the elephant and reporting back. And of course, there is the public moment. Newsrooms call, headlines form, people ask whether this is dangerous, which is a reasonable question whenever you say fast object and close pass in the same sentence. The reassuring answer is that the very path that proves it came from another star system also proves it will not stay. It is the cosmic equivalent of a tourist bus that never leaves the highway. You can wave, you can measure, you cannot get run over if you are not in the lane. Discovery Day is where the tone of the entire campaign is set. Get those first hours right, and you lock in a timeline of data that will feed everything that follows. How we understand its path, what we learn about its surface, whether it grows a tail, and how we might dream about meeting the next one with a ready spacecraft. The universe rarely schedules appointments. It prefers drop-by visits that demand you be ready on any given Tuesday. Next up, we will unpack exactly what makes this traveler interstellar and how astronomers can tell, from first principles, that it is not a local. Buckle up for Chapter 2, the fingerprints of a visitor who does not have a return address. If Chapter 1 was the gasp, this is the explanation between breaths. We have a speck of light on a crowded stage, and the big question is simple. Is this a hometown rock, doing a weird dance, or a traveler from far beyond our star's neighborhood? The answer rests on 3 fingerprints you can spot even without a lab coat: the shape of its path, the speed it carries before the sun even says hello, and an origin story that does not match our family album. It showed up without a return address and still made the guest list. First fingerprint, the path. Imagine tracing an object's route through space the way you might follow a skater's line on ice. Most local objects carve neat loops around the sun, closed tracks that you could follow again and again like a race course. Those loops are what planets and most asteroids do. Some comets draw long, stretched loops that take ages to finish, but they are still loops. An interstellar visitor, by contrast, draws a swoop that never closes. It comes in from the dark, curves around the sun, and leaves on a fresh heading, never to repeat the move. If a loop is a ring tossed on a peg, this is a boomerang that does not come back. In orbital language, that swoop is called a hyperbolic path, but you can think of it as a one-way road laid through a roundabout. The curve is real, but the exit is guaranteed. Why does the shape matter so much? Because the sun is a collector. Anything that is not moving fast enough to escape becomes a long-term guest. A loop means the sun won the tug of war. An open path means the visitor won, even while turning its head briefly to look at the light. The curve around the sun shows that gravity took a swing, but the visitor's momentum was stronger. The path is geometry. telling us a story about who holds the leash. Second fingerprint, the speed that does not care about borders. Far from the sun, where its pull fades, every object has a kind of cruising pace. Local bodies inherit their pace from the sun's family dynamics. They were born in the same rotating nursery and tend to move with the flow. An interstellar traveler shows up with a pace of its own, a cruising speed that would carry it straight through the outskirts, even if the sun were not there at all. In the trade, that distant pace is a key clue. It is the difference between rolling downhill because gravity gave you a push and blazing in because you were already sprinting. We can sense this by measuring how the object's speed changes as it approaches and then leaves. Local visitors tend to arrive without enough juice to walk away forever. The sun lends energy on the way in and takes it back on the way out. The tab balances to zero and the loop closes. An interstellar guest arrives with a surplus in the bank. The sun can bend the checkbook, but cannot cash it out. That leftover, far from the sun's reach, is the signature. It is cosmic body language that says, I was traveling before you met me, and I will keep traveling long after. Now for the third fingerprint, the origin that does not match local family history. Our solar system has clans. Asteroids largely keep to certain belts. Comets that spend most of their time in the deep cold come from a vast shell, far beyond the planets. A hazy reservoir of small, icy bodies. Even when a comet drops inward for a dramatic close pass, its path lines up in patterns we have seen before. Think of family accents. You can often tell where someone grew up by the way they speak. Interstellar objects do not speak with a local accent. Their incoming direction can be tilted in odd ways, relative to the plane where the planets dance. Their timing does not line up with typical long-period comets. Trace their path backward, and you do not land in the known hangouts of our clan. Astronomers try to rewind the tape and ask, where in the wider sky did this thing come from? That is harder than it sounds, because tiny uncertainties inflate as you play the movie backward. A small nudge here becomes a big shrug a few years earlier. Still, by averaging over many possibilities, you get a general incoming corridor. If that corridor does not line up with the usual comet highways, and if the speed surplus is there, and if the path refuses to close, the case builds. You do not need a dramatic reveal. You need the quiet weight of 3 lines of evidence pointing the same way. All of this might sound like jargon wrapped in mystery. So let's strip it to picture book clarity. Draw a circle for the sun. Sketch neat ovals for the planets. Now draw a long curve that starts far away, skirts the circle, and leaves for the edge of the paper. That is the path. Add a big arrow on the incoming side that does not shrink to nothing, even when the curve is far away. That is the speed that belongs to the traveler, not to the sun. Finally, tilt the curve so it slices through the page at a strange angle, not matching the ovals. That is the origin mismatch. Put those 3 drawings together, and you have the calling card of a body from another star. One more twist. Sometimes the coma of gas and dust around a comet can give it a small push, like a leaky rocket, that can fake a speed change. To guard against that trick, observers watch the light pattern closely. If there is a faint envelope of vapor, you account for its nudge. If there is no sign of outgassing, but the path is still open and the surplus pace is still there, the interstellar label stands even taller. It is not just a strange local, it is a stranger entirely. When you add up the clues, the picture is crisp. A visitor that curves past the sun without settling down, that carries its own cruising pace from the deep, and that approaches from a direction that does not trace our family map. That is how you know you are watching a traveler between stars. Next time, we will trade the sky map for a calendar and chart the flyby itself. When, how close, and what that timing lets us learn on the run. Chapter 3. The Flight Plan. Dates, distances, and drive-by science. Open your mental calendar and grab a pencil. Our visitor is not here for a lingering vacation. It is blowing through town on a timetable that would make a bullet train sweat. Space has no speed limits, but this thing still drives like it is late for a meeting with Jupiter. To make the most of it, astronomers break the flyby into 3 acts: the long inbound, the hairpin at closest pass to the Sun, and the fading outbound, each with its own sweet spot for different kinds of science. Act 1 begins long before the headlines, when the object is inbound and faint, like a distant car on a desert highway, with its headlights barely visible. This is the reconnaissance phase. Distances are enormous, so we trade detail for context. By watching how its brightness changes night to night, we sketch out a rotation rhythm and get early hints about shape. The metaphor is listening to a train before you can see it, catching the cadence of wheels over rails. Telescopes favor long exposures and patient tracking to tease out a signal from the sky's glow. The angle between the object, the Sun, and Earth is wide, which means we see more of its unlit side than its face. That sounds unhelpful, but it is perfect for clues about surface texture, because rough terrain scatters light differently than smooth ice. As the calendar pages flip, Act 2 rushes up, closest pass to the Sun. Picture a roller coaster cresting a drop. Gravity is the engine now, and the visitor is diving, heating, and, if it is the icy kind, beginning to shed a thin veil of vapor and dust. The key word for observers is timing. There is a brief window when the object is brightening faster than a weather app can update, yet still far enough from the Sun's glare to catch with cameras. Here we switch to rapid cadences, stacking many short exposures to follow every twitch. Spectrographs come out to sniff the light, separating it into colors the way a prism paints rainbows on a wall. Those colors carry fingerprints of whatever is boiling off the surface. And though the outflow might be thin, even a whisper can be heard if the microphone is good and the room is quiet. At the very bottom of the dive, the object skims through its point of closest approach to the Sun, the tightest part of the curve where the path bends hardest. For a few tense days, the geometry is lousy for earthbound eyes. The visitor is lost in the Sun's neighborhood, like a plane crossing behind a spotlight. Ground observers cede the stage to space telescopes that can peer closer to the glare, and to solar observatories that specialize in watching faint things near fierce light. We are not idling, though. We are modeling the path and predicting where to point the moment it reemerges, because the outbound act is packed with opportunity. Act 3 starts as the visitor swings outward, and the phase angle improves, meaning we now see more of its sunlit face. This is the portrait session. The light curve gets cleaner, the rotation signal steadier, and if there is a tail, it stretches in a way that tells us about grain sizes and how the solar wind is pushing. Polarimeters step in to measure how light waves twist and scatter after bouncing off dust, a subtle effect that nevertheless reveals whether the surface is frosty, sooty, or something in between. Radar could join the party if the distance shrinks enough and the size is cooperative, because radar is the one trick that turns a dot into a silhouette. Even without radar, high-resolution, lucky imaging, snatching brief moments of steady air, can sharpen the point into an elongated smudge that hints at shape. You asked how close this road trip takes our visitor to other landmarks. Think of the solar system as a set of nested lanes. The innermost 2 lanes belong to Mercury and Venus, then Earth's lane, then Mars, with a broad median before the domain where Jupiter rules. Our traveler threads those lanes without signaling. It does not need to pass right next to a planet to make the journey dramatic. A skim just inside Earth's lane can still be many times the Earth-to-Moon distance, safely far, yet scientifically mouthwatering. That kind of proximity is ideal for parallax measurements, where observatories, separated by continents, watch the position shift against background stars. 2 viewpoints turn a flat map into a depth chart, tightening distance and speed. Now about that meeting with Jupiter. Even if the path never goes near the giant directly, Jupiter's gravity is the neighborhood watch captain of the outer system. Its presence shapes the broad architecture of orbits, and a visitor's course is calculated with those subtle tugs in mind. On the outbound leg, as the object climbs back through the lanes, the giant's slow hand still nudges the curvature by a hair. We read those tiny changes like pencil annotations on a route map, confirming the flight plan and improving predictions for the future path as it fades. What makes this whole timeline so valuable is the way different science fits into different slots. Early inbound gives rotation and crude size. The pre-sun sprint offers chemistry and the first hints of surface layers if any material escapes. The immediate post-sun climb shows how outgassing, if present, evolves as heating subsides. The mid-outbound phase, when the viewing angle is flattering and distances shrink, is for shape, spin axis orientation, and tail physics. And the late outbound is the quiet epilogue, where we squeeze the last drops of positional precision to refine the trajectory for the archives. We can also get lucky with occultations, those magic moments when the object drifts in front of a background star and briefly blinks it out. Even a scratch of darkness on a light curve can carve a razor-sharp outline of size and reveal jets or fragments if the edge looks jagged. Predicting these events is like forecasting a moving keyhole shadow sweeping across Earth. When it lines up with telescopes, we learn far more than a single snapshot would allow. All told, the flight plan is less about a single headline moment and more about an orchestrated chase across months. Each night adds a brushstroke. Each instrument adds a texture. By the time the visitor fades toward the boundary where sunlight is a rumor, we will have a travel diary. When it arrived, how close it threaded the lanes, how bright it flared, and what it whispered about its surface as it blazed past. Next, we zoom in on the traveler itself, the solid heart, the hazy breath, and the dusty train, in a chapter all about anatomy, without spoilers from any other act of this story. Chapter 4, Anatomy of a Stranger, Nucleus, Coma, and Tail. When a cometary visitor sweeps into view, we are not looking at one thing. We are looking at a layered performance, a solid heart that stays quiet, a breath of vapor that refuses to mind its own business, and a drifting scarf of dust that the sunlight grabs and flings behind. It is the only tourist that brings its own fog machine. To make sense of what we see, astronomers peel the scene apart, asking which photons bounced off rock and ice, which passed through a cloud of gas, and which ricocheted from powder so fine it behaves like smoke. Let us start with the nucleus, the core you never quite see directly. Imagine a lumpy, charcoal dark snowball with cliffs, pits, and crusted plains. It spins, it warms, and it cracks. The surface is not pristine sparkle. Centuries of sunbaths bake a crust that can trap ices beneath. When a patch finally warms enough, gas jets burst through, and the nucleus vents like a tiny geyser. From far away, that solid body is just a pinpoint. Its true size hides behind the light of the surrounding cloud, and that is where the slipperiness begins. We want to know whether we are dealing with a pebble or a mountain, but the fog machine keeps turning up the dimmer. Next comes the coma, the shroud of gas that expands from the nucleus as sunlight shakes loose molecules from the surface or from freshly exposed grains. The coma is not a tidy sphere. It is a messy, breathing envelope, thicker where active vents face the sun, thinner on the night side, and constantly stirred by rotation. Because the gas is basically invisible except in certain colors, we often witness it indirectly through what it does to dust and through faint glows at specific hues that belong to certain molecules. The practical effect is that the coma acts like a floodlight, making the whole object seem larger and brighter than the core alone could manage. A small nucleus with a vigorous coma can masquerade as a giant, while a big but lazy nucleus sulks in the dark. Trailing behind is the dust tail, a long streamer shaped by sunlight and the faint push of solar wind. Dust grains leave the scene at different speeds depending on size. Pebble-sized bits cling close, while powder-sized specks get flung into sweeping curves. The tail you can photograph is mostly sunlight bouncing off this drifting confetti. Because the dust cross-section is huge compared with the nucleus, the brightness you measure can be dominated by crumbs rather than the core. This is wonderful for studying the crumbs and awful for sizing the core. Imagine estimating the size of a campfire by the glow of the smoke instead of the logs. So how do we wrestle the nucleus out of the glare? One approach is to catch the traveler when it is still cold and quiet, before the fog thickens. But even then, distance blurs the view. Another tactic is to observe in thermal infrared, where warm objects radiate their own glow. A rough measure of heat combined with reflected sunlight can separate a dark big body from a bright small one. Yet here lurks another gremlin. How reflective is the surface? A dark nucleus needs to be larger to reflect the same amount of light as a shiny one. If you do not know the reflectivity, your size estimate can slide like a sock on a waxed floor. Angles matter too. When the sun and earth line up just so, dust can forward scatter light toward us, turning the coma into a mirror that exaggerates brightness. That effect is fantastic for spotting faint material, but terrible for taking the nucleus's measure. Add rotation to the mix, and the light can pulse as brighter or darker terrains turn toward us, further confusing the tape measure. We can model these effects, but every extra knob on the model is another way the answer can wander. Inside the coma, the physics is delightfully chaotic. Gas lofts grains, grains cast shadows, shadows cool the surface and move the hotspots. And the cycle repeats. Jets carve fans and spirals in the coma that shift with the spin of the nucleus. Those patterns act like clock hands for rotation and reveal where venting regions sit. They also give away something about the texture of the surface. Coarser grains need more push to escape, so if the coma favors fine dust, the crust might be weak and crumbly. If stones show up, vents are punching hard through stronger layers. The tail is its own laboratory. Sunlight pressure sorts grains by size in a graceful, predictable way. So the curvature and width of the tail tell us about the distribution of dust sizes. Leaving the nucleus, faint striations or kinks can betray episodic outbursts, like a sneeze in the middle of steady breathing. Farther out, the gas tail, if present, points more directly away from the sun, shaped by the solar wind, and it carries information about ionized species and magnetic fields. The duet of dust and gas tails is a running commentary on how the traveler is interacting with its new hot environment. Every now and then, the fog parts for a heartbeat. When the visitor passes in front of a distant star, it can clip a tiny bite out of the star's light. That momentary nip sketches a true edge of the coma, or, if the timing is perfect, a hint of the nucleus itself. Even a single clean silhouette can anchor size models that would otherwise drift. Another gift arrives when the activity quiets down on the outbound leg. As the coma thins and the tail fades, the stubborn pinprick at the center finally starts to dominate. Those late snapshots, compared with earlier ones, fence in the nucleus's dimensions and give us a sharper picture of the traveler's spin. In the end, anatomy is a puzzle of subtraction. We measure too much light, then carefully remove everything that is not the core. We track shifting textures in the fog to infer where vents breathe. We follow the tail's graceful sweep to read the sizes of grains and the rhythm of outbursts. Piece by piece, the stranger becomes a person we can describe, a certain size, a certain spin, a certain style of shedding. With that frame in place, we are ready to talk ingredients. Next time, we open the pantry and sniff the spices. What ices, what gases, and what traces whisper about the kitchen where this traveler first froze. Chapter 5. Chemistry Without the Headache. Open the freezer section of the cosmos, and you will find our traveler stacked with ingredients like a long-forgotten meal prep box. There is the big bag of water ice, the solid chunks of carbon dioxide, a dash of carbon monoxide that behaves like a spicy pepper, and a rack of lesser-known seasonings with names that sound like a sci-fi menu: methane, ammonia, methanol, formaldehyde, hydrogen cyanide, and a scattering of complex organics. Photosynthesis is plants saying we invented solar panels first. Comets are the deep freezers of the galaxy, saying keep the receipts. Let us start with the headliner, water ice. It is the base stock of many comets, and it tells us about temperature history, the way a tree ring tells you about rainy seasons. If water ice begins to lift off early, far from the sun, that means the surface is porous, the grains are fine, and sunlight can sneak down to warm hidden layers. If it waits until the visitor is much closer, the crust is tougher, or the grains are larger and packed tight. The timing of that first breath of water vapor is like a kitchen timer going ding. It reveals how insulated the pantry was, and whether the top layer is fresh or baked into a rind by past warming. Now to the cold kings, carbon dioxide and carbon monoxide. They are more eager to escape than water, which means they can start venting even when the sun is only a rumor on the horizon. If we see early activity rich in carbon monoxide, we infer that parts of the nucleus formed in a deep freeze, where even the most delicate ices stuck around. Think outer nursery, far from any warm star, possibly inside a shadowed pocket of a planet-forming disk, a coma dominated by carbon dioxide. On the other hand, hints at a kitchen that was cold but not bone-chilling. Perhaps a region just beyond where water freezes, where carbon dioxide can still settle out in generous supply. The balance between these two gases is a thermometer written in vapor. Trace ingredients refine the recipe. Methane and ammonia speak to chemistry that happened in the dark with little starlight, where hydrogen saturates carbon and nitrogen. Methanol and formaldehyde suggest that simple molecules met on grain surfaces coated with frost and reshuffled under gentle ultraviolet nibbles. Hydrogen cyanide is a badge of more energetic processing, as if the pantry sat near a young temperamental star for long enough to spark livelier reactions. When we find sulfur-bearing molecules, we suspect that the stove had a whiff of volcanic spice in its past, meaning the grains that built the comet may have sampled material from warmer inner regions before being flung back to the cold. Then, there are the organics that refuse to fit neatly into a one-word name. Some are gunky, tar-like substances that space chemists nicknamed tholins. They are what you get when sunlight and charged particles play mix and match with simple ices over long stretches of time. Spread across a surface, they can darken the skin, soak up sunlight, and change the way heat moves through the top layers. That, in turn, changes when and where the comet breathes. Chemistry is not just a list of ingredients. It is a thermostat and a dimmer switch for the whole performance. The noble gases, argon and its quiet cousins, are the wallflowers that tell the best stories. They do not react easily, so if they are present, they arrived early and stayed put. Detecting them is hard, like hearing a whisper in a concert hall. But when we do, they pin a flag in the temperature map. Argon, for instance, only clings if the freezer stayed extremely cold throughout assembly. Find it, and you have evidence for a birthplace that never flirted with warmth. Isotopes add a detective's flourish. Heavy hydrogen mixed into water, heavier carbon tucked into carbon monoxide, and similar subtle markers can act like regional dialects. A higher fraction of heavy hydrogen points to formation in deeper cold, where reactions favor that heavier version. Lower fractions nudge the origin toward milder zones. Because these ratios change slowly and resist later edits, they are the fingerprints least likely to be smudged by the comet's later adventures. When combined across several molecules, they sketch not just a temperature, but a timeline of how the ice assemblage came together. How do we read all this without a lab bench? We let the light talk. Sunlight excites molecules in the coma, and they glow at colors that belong to specific bonds, like neon signs, advertising who is open. Instruments spread the light into a spectrum, and each bump and dip is a signature. Some telescopes read the warm glow in infrared, catching the soft purr of water vapor or carbon dioxide. Others listen in the radio, where rotating molecules broadcast at precise stations on the dial. All these signals ride on the same breeze from the nucleus, so we cross-reference them to see which vents breathe what, and how that menu changes with time and sunlight. What can these flavors tell us about the kitchen it came from? Picture a star being born inside a swirling disk of gas and dust, streaked with rings, gaps, and snow lines. Closer in, rocks cook and metals condense. Farther out, water freezes then carbon dioxide, then carbon monoxide, each crossing a line where that ingredient switches from gas to frost. Grains migrating through these zones collect layers like a pastry, and then jostling, merging, and gentle stickiness build the crumbs into larger bits. If our traveler is rich in carbon monoxide and argon, it likely formed beyond the outer snow lines, or at least spent time there before being assembled. If water dominates with a modest side of carbon dioxide and only a whisper of carbon monoxide, it was probably baked a little, maybe tugged inward and outward during its youth, sampling several shelves of the pantry before being stored. Even the absence of certain gases is a clue. If nitrogen is scarce, the disk where it grew up might have been depleted by early heating or stripped by a nearby hot neighbor star. If complex organics are abundant, the disk probably enjoyed long stretches of gentle ultraviolet light, rather than violent flares, favoring slow-cooked chemistry over flash fry. Put it together, and chemistry becomes biography. We are not just naming molecules, we are reconstructing childhood neighborhoods, travel history, and climate. It is a patient, delicious kind of forensics. Next time, we will leave the lab bench and join the pit crew. How a planet-wide network of telescopes and spacecraft coordinate to catch every whisper from a speeding, evaporating guest. Chapter 6. Telescopes Assemble. A global observing campaign. When an interstellar visitor streaks into town, astronomy turns into a heist movie where everyone has a specialty, and the clock is always ticking. Ground observatories bring brute collecting power. Space telescopes glide above the weather with the serenity of mountain monks. Instruments scattered around other worlds offer rare camera angles. Together, they form a cosmic pit crew, rolling out in seconds, swapping tools mid-lap, and handing off data like wrenches. If Chapter 5 was a chemistry tasting menu, this is the Kitchen Brigade in full choreography. Start on Earth, where the night is divided by longitude like relay lanes. As dusk falls in one country, a partner on the next continent is already warmed up. Big mirrors on dry mountaintops drink faint light, while nimbler telescopes chase quick changes. Adaptive optics turns wiggly air into calm seas by flexing mirrors hundreds of times a second, sharpening starlight until a point becomes a true point instead of a puff. Polarimeters measure how that light twists after scattering off dust, a subtle tell that can distinguish frosty crusts from sootier skins. High-speed photometry grabs the heartbeat of rotation, bottle-feeding photons minute by minute to watch for blips that betray jets and irregular shapes. Down in the radio domain, wide dishes listen for whisper-thin broadcasts from rotating molecules, mapping out where the gases pool and flow. Each of these stations plays to its strength, and none can cover the sky alone. Now lift off. In orbit, telescopes float above clouds and turbulence, catching wavelengths that never reach the ground. Ultraviolet cameras read the bright neon of gases set aglow by sunlight, the way a black light makes hidden ink shout. Infrared instruments collect warmth directly, turning thermal glow into maps of size and texture. They are the night vision goggles of the fleet. Without atmospheric water vapor to drink those colors, space observatories can tell a small, shiny surface from a large, sooty one with far more confidence. X-ray and extreme ultraviolet eyes, perched on solar-watching spacecraft, add a surprising twist. When fast solar particles slam into the comet's coma, they trigger faint glow that sketches invisible boundaries where the wind of the sun meets the breath of the traveler. Space has no speed limits, but our hardware respects one rule: you get the best answers when everyone looks at the same thing in different ways at the same time. Then there are the remote outposts, a camera orbiting Mars, or a station riding near a gravitational balance point between Earth and the Sun, can watch from angles we cannot buy from the ground. Imagine trying to understand a parade using only curbside snapshots. A drone view changes everything. A Mars orbiter can photograph the visitor head-on, while Earth sees it side-lit, letting teams untangle three-dimensional shapes from two-dimensional smears. A solar sentinel can stare closer to the glare, catching the comet during the tight bend around the sun, when ground telescopes must look away. These side doors matter because some of the most revealing moments happen when the geometry is worst for any single vantage point. Coordinating all of this is its own science. Alerts fly through networks that astronomers watch like sports scores. One team posts a light curve, another adds a spectrum, a third announces that an occultation, the brief blink of a background star, is about to sweep over a chain of observatories. Local weather writes its own plot twists, so redundancy saves the day. Two telescopes separated by an ocean can rescue a plan from a storm front. Time allocation committees that usually plan months ahead switch to sprint mode, carving out emergency slots so a space telescope can pivot. On the ground, robotic observatories accept scripts by the hour, scanning in patterns optimized for the night's priorities. Data does not nap either. Pipelines digest images before the coffee cools, spitting out calibrated files that anyone on the project can analyze from anywhere with an internet connection. Different wavelengths act like detective lenses, each revealing a fingerprint the others miss. Visible light tracks dust, the bright confetti that dominates appearance. Infrared traces warmth, so it weighs the nucleus more fairly and exposes cold gas species that hide from optical cameras. Ultraviolet spotlights, fresh water, carbon dioxide, and the fragile fragments that form when sunlight breaks molecules apart. Radio links individual identities to precise speeds, a way to watch gas outflow as if it carried tiny barcodes. X-ray and extreme ultraviolet mark the boundary where the solar wind steals electrons, outlining invisible magnetism like dew, outlining spider silk. Put the pieces together, and you have not just a picture, but a dossier. The choreography gets fancy around occultations and close approaches. Predicting a star blink is like forecasting a moving keyhole shadow across Earth. Observatory coordinators place telescopes along a projected path on highways, hills, and even school rooftops. For a few heartbeats, the visitor draws a crisp edge across starlight, letting teams measure size and, if the edge is jagged, tiny jets or fragments during close Earth flybys. Still respectful, still far, radar teams try to ping the nucleus, while optical teams tighten the shape and spin. Meanwhile, spectroscopists schedule synchronized exposures to see whether an outburst changes the menu of gases minute by minute. It is the astronomy version of a pit stop. Quick, precise, everybody on task. Do not overlook the citizen scientists. Skilled amateurs with backyard observatories fill gaps the big facilities cannot cover, especially in the hours between professional windows. Their images, when carefully calibrated, extend light curves, catch surprise flares, and sometimes snag the only clear view during a weather-cursed night. Think of them as volunteer firefighters in a town that occasionally welcomes meteoric parades. All this teamwork pays off in ways no single instrument could match. A spike in infrared brightness can be linked to a surge of carbon dioxide in ultraviolet, then mapped to a discrete jet seen in polarized visible light, then timed against a rotation phase found in high-speed photometry. Once those threads are woven, the story stops being a guess and becomes a narrative. A vent woke up on the morning side, belched fine grains, heated the surrounding terrain, and then quieted as the nucleus rolled on. The interstellar guest moves on, but the pit crew does not disband. The data live on in public archives, where future teams will reprocess them with better tools, testing new ideas against the old photons. Next time, we will explore one possible plot twist for any active traveler. What happens if the nucleus cracks, and why a breakup can be the most revealing moment of all. Chapter 7, What if it fragments? Lessons from earlier visitors. Picture our visitor as a layered truffle, a crusty shell hiding colder sweets inside. Now imagine the shell cracking mid-journey. To the scientist, that is not disaster. That is a tasting flight delivered by fate. Fragmentation turns a single faint target into a family drama. And from that drama, we learn what factory built the truffle, how tough the shell really was, and how the pieces behave when the script goes off-road. Why do comets and comet-like bodies break? 3 usual suspects show up in the lineup. First, tidal stress. Pass too close to a heavyweight like Jupiter or the Sun, and gravity tugs one side harder than the other, the cosmic equivalent of trying to carry a watermelon with buttered hands. That is how a famous chain of fragments once lined up and dove into Jupiter one after the other, turning a single visitor into a string of fireworks across a giant sky. Second, thermal stress. A crust that has slept in deep cold wakes up fast under sudden sunlight. Surfaces expand, buried layers lag behind, and cracks spider through like ice on a warming pond. Third, spin up. Jets acting as tiny thrusters can gradually twist the body faster until centrifugal stress overmatches the glue that holds rubble together. Slow twirl becomes fast tumble, then pinch, then snap. Each cause leaves a different set of breadcrumbs. Tidal splits tend to produce trains of pieces that share nearly the same path, stretched along the direction of travel. Thermal failures can be more chaotic, with chunks flying from sunlit cliffs and vents that gave up all at once. Spin breakups often show twin or triplet pieces separating along the equator of the parent, like a pizza trying to slide off its peel. The pattern matters because it lets us work backward to the strength of the material. A body that survives a brisk spin was sturdier than a loose rubble pile. A body that comes apart under mild heat was more fragile than it let on. Why does a breakup help us size the core? 2 reasons. First, the brightness game changes. When a nucleus shatters, the total reflecting area can surge as fresh surfaces and swarms of chips flood the coma. That spike, tracked over days, tells us how much new area appeared, which relates to how much material left the main body. Second, the fragments themselves become yardsticks. If we can separate their light from the dust cloud and follow how they fade, we can estimate their sizes. Add them up and compare with the pre-break brightness and the thermal footprint, and you can bracket the original. It is like reconstructing a vase by measuring all the shards on the floor. Cracks also expose untouched interiors. Before a breakup, we mostly sniff what leaks through ancient vents and weathered crust. After a split, we see vapor from layers that have never met sunlight. Spectra, taken in those first hours, can be wildly different from the weeks before. Unfamiliar ratios of gases, sudden appearances of delicate species that burn off quickly, and dust grains with textures that would have remained buried for centuries. These first light snapshots are the closest thing to tasting the dough before it was baked, and they can reset our understanding of where the visitor grew up. Past travelers have given us a field guide to chaos. Some disintegrated near the sun, in a dramatic fade, leaving only a dust rope to mark their passing. Others peeled like an orange, shedding big lobes that drifted downwind for months. A few fractured repeatedly, turning one breakup into a series. A main nucleus followed by a younger sibling, then that sibling becoming twins. Each episode fed hard numbers to models of strength, cohesion, and porosity. We learned that many small nuclei are not monolithic rocks, but gentle assemblies of boulders and frost, held together by weak gravity and sintered crust. We also learned that some are tougher than they look, enduring heat and spin levels that would have unzipped their cousins. If our interstellar guest were to split, the science windows would open and slam in quick succession. The very first day is for chemistry. Catch the newborn vapor before sunlight edits it. The next few nights are for kinematics. Watch how the pieces drift relative to each other. Their separation speeds and directions encode the push that tore them apart and the density that resists sunlight tapers. A week out, the dust cloud begins to sort by grain size under the nudge of sunlight, sketching elegant fans that let us measure the distribution of particle sizes, liberated by the crack. Later still, as the fragments settle into independent spins, we can time their rotations and look for secondary shedding, which tells us whether the pieces are still too fast for comfort. There are risks, of course. A shattered target is harder to track. Fragments fade faster than headlines and can be lost in glare or distance. The dust cloud can swamp measurements of the solid pieces, making it tricky to keep the calculation honest. Observing plans must pivot overnight. Teams focused on a single point source need to switch to chasing multiple moving specks, but the payoff is a masterclass in real-time geology without ever landing. Breakups also refine navigation math. Before a split, non-gravitational pushes from vents act in patterns tied to a single spin. After a split, each fragment carries its own jet geometry. By fitting the changing paths, we can back out thrust levels from outgassing and thus infer surface activity and mass. That means better estimates of density, which in turn whisper about how much empty space lives between the building blocks inside. Speculating within reason. If our traveler fragments early, when it is still distant, we could stage a long campaign to watch sibling pieces evolve on separate diets of sunlight. If it waits until the tight turn near the sun, space-based observatories get the starring role, and the chemistry sprint becomes a breathless dash. If it holds together until outbound and then cracks, we score the rare chance to catch interior ices in a cooling phase, a natural experiment in how quickly fresh surfaces go quiet. Either way, fragmentation is not the end of the story. It is the plot twist that reveals character. A split tells us how the body was put together, how it handles stress, and what it hides inside. With those clues in hand, we can think bigger. What could shards like these do if they wandered into a young star's construction zone? That is where we are headed next. How interstellar rubble might serve as seeds for worlds, turning cosmic breakage into creative beginnings. Chapter 8. How interstellar rubble may build planets. Imagine a newborn star wrapped in a hazy, glowing pancake of dust and gas. Grains swirl, bump, and try to stick, but most of the time, they behave like shy party guests. A few awkward collisions, then everyone drifts apart again. Nature gets stuck at the crumb stage because tiny grains bounce instead of bonding, break when they hit too fast, or spiral inward toward the star before they can grow. Planet formation is cosmic group work. Someone has to bring the glue. Enter the wanderers, sturdy chunks from beyond, drifting through space like seeds with their own hard shells, ready to change the social dynamics of the disk. Here is the idea in plain terms. A young disk is a storm of pebbles, sand, and gas. Small pieces try to grow by sticking, but the roadblocks are many. When an interstellar object wanders in, anything from a boulder to a mini mountain, it can act as a shortcut. Instead of coaxing grains to climb the ladder, one rung at a time, the disk suddenly has a pre-built step stool. If the intruder slows down enough to be captured by the gas and dust, it becomes a nucleus that nearby pebbles can slam into and stay. Growth gets leverage. The difference between maybe someday and now we are getting somewhere can be a single tough core, making the neighborhood stickier. How does capture actually happen? In a young system, gas is thick enough to matter. A visitor passing through feels drag, like riding a bike into a headwind. If the path carries the object through denser gas or dust lanes, it loses energy and can drop into a bound orbit. That sounds delicate, but remember, disks are wide and live for millions of years. Even rare events have many chances. Once captured, the object experiences an ongoing drizzle of pebbles that drift inward through the gas. Those pebbles are the disk's conveyor belt of building material. The hard visitor now becomes a collector's plate. As pebbles spiral past, the gravity of a moderate-sized core can gather them more effectively than bare gas and dust alone. It is like setting a small rock in a river and watching leaves eddy in its wake. The local flow changes, concentrating material that would have rushed by. With enough concentration, a feedback loop begins. More pebbles mean more mass bends the flow more strongly, and the collector grows faster. This is growth by scavenging rather than by delicate adhesion. You do not need perfect glue if you have a net and patience. There is another boost. Turbulence can herd pebbles into pockets of higher density, and a solid intruder sitting in one of those pockets acts like a lightning rod for debris. When the pocket collapses under its own concentration of solids, the intruder ends up as the seed of a larger clump. In effect, the disk lends a hand, corralling material, while the seed provides a place to land. It is construction, with both scaffolding and gravity, doing the heavy lifting. What about composition? A seed from another star system is not just a rock with ambition. It carries its own recipe of ices and minerals. If it settles in an outer, colder zone, it can contribute volatiles that affect how the emerging body retains an atmosphere, how it heats from within, and what chemistry happens on and below the surface later on. A seed settling closer to the star brings refractory material that survives heat better, shaping the kind of crust that forms. In either case, the seed's recipe adds diversity to the local pantry. And diversity is exactly what we observe when we look at exoplanets. A mess of sizes, densities, and atmospheres that suggests the starting materials were not perfectly uniform. Now, picture a bigger visitor, something closer to a mini planetesimal than a pebble, threading the disk. It begins to carve a faint wake as it orbits, exciting ripples in the gas. Those ripples can trap drifting pebbles the way waves pile leaves along a shoreline. Trapped pebbles collide gently and can stick more readily than in the general churn. The wake becomes a workshop. Over time, that workshop can build a skirt of material around the seed, thickening it into a body that has its own gravity well strong enough to start pulling in larger fragments. Past a certain point, growth is not just steady, it is hungry. At the small end, even shard-sized wanderers matter. A shower of grit from an interstellar fragment can fertilize wide areas of a disk, adding surfaces for frost to collect and chemistry to proceed. Grains with icy coatings stick better than bare grains, so a spritz of new frost can tip the balance from bouncing to bonding. Think of it as dust with upgraded Velcro. Is this only an outer disk story? Not necessarily. Inner regions are warmer and more hostile to ices, but they are also densest in solids. A captured seed can survive there if it is rocky enough, becoming the anchor for a future terrestrial-class world. A single rugged core can stabilize its neighborhood, sweeping up hot debris that would otherwise grind itself down. Over many orbits, the result can be a dry, dense planet that owes its existence to a traveler that refused to keep going. The broader implication is poetic. Stars may share building blocks. If even a small fraction of the rubble drifting between systems gets captured in young disks, then the genetic tree of planets is part local, part imported. That might help explain why some planetary systems look as if they took familiar ingredients and cooked them into surprising shapes. A few borrowed seeds can steer outcomes in ways that slow, strictly local growth cannot. Of course, not every visitor becomes a citizen. Many pass straight through, tugging lightly at the gas and vanishing back into interstellar dark. But those that do take up residence can change the timeline. Instead of waiting for dust to debate the merits of sticking for a few million years, a seed can start the party now. The disk gets a head start on making planetesimals, and those planetesimals clear lanes, build cores, and eventually light up the system with worlds. So, if a wandering object gives a young star's disk a leg up, what could we do with a wandering object passing near us right now? In the next chapter, we trade nursery tales for engineering dreams, using a fast traveler as a ride, and what it would take to hitch a probe to a comet that is in a hurry. Chapter 9. Hitchhiking the Stars. Using 3IATLAS as a ride picture, a tiny spacecraft hanging back like a surfer, sizing up a fast, unruly wave. The wave is a living thing. Ice warming, gas venting, dust spraying, magnetic fields tangling with sunlight. Our craft edges closer, reaches out a clever hand, and grabs hold for the ride of a lifetime. It is the ride share you cannot rate, but absolutely want to catch. There are two broad ways to hitchhike. One is literal, touch the surface and anchor to the nucleus, so your path becomes its path. The other is more like kite surfing, Never land, but use the comet's outflow and electric environment as an invisible wind to pull you along. Both sound audacious. Both are surprisingly plausible if you think small, nimble, and patient. Let us start with the grab. Anchoring on an active, low-gravity body is like trying to plant a tent stake in a trampoline while someone keeps jumping. The surface could be powder, crust, or pebbly cement, and it will not tell you which until you arrive. A harpoon might bounce if the crust is rock hard, or sink too far if the top layer is fluff. Engineers counter that uncertainty with a toolbox. Microspined feet that hook onto rough grains like gecko fingers, small eye screws that warm as they turn so they melt in and refreeze, and springy pitons that wedge without cracking brittle layers. The trick is to touch down with the gentleness of a sleeping cat so you do not rebound into solar orbit. Even after you stick, the ground does not sit still. Jets can erupt meters away and shove your little lander with invisible hands. The fix is to spread the load and stay flexible. Picture a tripod with shock absorbers, a waist belt of tethers, and an automatic lean-in reflex that shifts the center of mass toward the push rather than fighting it. You do not outmuscle a comet, you dance with it. Power is next. Close to the sun, solar panels are happy. Farther out, they sulk. A rider needs a mixed diet: sunlight while it is bright, a compact battery for sprints in shadow, and, if you can afford it, a steady heat source that does not care about seasons. There is also free energy passing by every second. The vented gas itself, a small intake, could gulp that flow and feed a cold gas thruster, turning the comet's breath into steering puffs for hovering or attitude control. It is not glamorous, but it is the space equivalent of catching rain in a cup. Communication is an exercise in humility. Dust coats everything. Antennas need to sit high on masts, with self-clearing covers that shake or flick off grains like a wet dog. Pointing is a headache, because the nucleus can tumble in ways that are more interpretive dance than ballet. The elegant solution is a two-piece system: a tiny anchor on the surface that does the sampling, and a free-flying relay box a safe distance away, connected only by radio. The relay keeps a steady posture for deep space links, while the hardy anchor hugs the chaos and whispers upward. If a jet shoves the lander into a nap, the relay still phones home. But what if we never land? Enter the kites. A comet's coma is a flow of neutral gas and ionized particles streaming outward. If your spacecraft carries a loop of current, a magnetic hoop that makes its own mini magnetosphere, it can feel a drag where charged particles try to flow through that invisible bubble. Tilt the hoop and you get a sideways tug. It is weak, but space is patient. Similarly, you can pay out long, thin, positively charged tethers that push back on incoming ions. That electric sail does not need reaction mass. It eats the wind and smiles. In the coma, the flow radiates outward from the nucleus, so a properly oriented kite can loiter near the object with very little propellant and even surf to a new vantage point when a jet turns on. The elegance of kiting is that you never share the nucleus's tumbles or its sandblasting at point-blank range. The downside is you must manage an environment that changes by the hour. Gas density rises and falls as patches rotate under sunlight. That means your tug varies like a heartbeat. Autonomy becomes your secret sauce. The craft senses local wind and adjusts tether charge or coil current on the fly, the way a bird trims feathers in gusts. Think quick, act small, and never wait for ground control to approve every twitch. Dust is the ever-present hazard. Even tiny grains at cosmic speeds punch above their weight. A hitchhiker needs a sacrificial bumper at the front, a thin shield that turns incoming grains into harmless puffs before they reach the good stuff. Optics hide behind shutters and peek out only when needed. Any surface that must stay clean wears a vibrating skin to shake off clingy particles. For the electric sail option, dust that sticks to charged tethers can be trouble, so the tethers need a gentle self-bake mode to warm and release grime. Navigation is a game of shadows and glimpses. Close to the nucleus, star trackers get confused by dust glow. The fix is a trio of local tricks: a wide-angle hazard camera that locks onto surface landmarks, a tiny laser rangefinder that reads distance directly, and a nose sniffing sensor that listens for gas density so it can ride the flow like a river pilot. Layer those cues and you can fly blindfolded through a snow globe. What would we do once we are aboard? A tiny rider might sample freshly lofted grains, bake them in a pocket oven, and send back the smells. It could plant temperature pins at different depths to watch heat pulse into the surface over a full rotation. A kite probe could map the shape of the invisible boundary where the solar wind meets the coma, following it as activity rises and falls. None of this needs a heavy lab, just well-chosen, simple instruments and relentless observation. The hardest part is timing the merge. You get one chance to match speeds and either latch or settle into a stable kite stance. Miss it, and the visitor is already half a sky away. That argues for very small spacecraft that wake up fast, accept rough conditions, and treat a successful minute as precious, a successful hour as a feast, and a successful week as legend. Hitchhiking is not a replacement for classic missions. It is a new attitude. Use what the comet gives. Do not fight what you cannot change, and keep the hardware light on its feet. If that philosophy clicks, the next interstellar passerby is not just a headline, it is a lift. And if we want a real shot at boarding, we need a playbook and a kit on the shelf. Next chapter, we sketch that kit. A rapid response mission built for speed, simplicity, and showing up before the party is over. Chapter 10, the rapid response mission. We wish we had imagined a phone on a wall in mission control with a single label, Interstellar Visitor. When it rings, the countdown starts, not to launch a decade from now, but to roll a spacecraft out while the headlines are still hot. The blueprint is not a mega rocket opera with a cast of thousands. It is a tight jazz combo, a proven spacecraft bus off the shelf, a solar electric booster that sips instead of gulps, and a travel kit of instruments that fit in a carry-on. In space exploration, being early beats being fancy. Step 1 is cultural, not technological. Commit to calendar speed as the prime requirement. If a craft can leave Earth within a few years of discovery, it wins even if it lacks every bell and whistle on your wish list. That means we pre-build the bones. Keep a small stock of standard spacecraft buses in clean storage, the way emergency services keep rescue vehicles fueled and ready. The bus has reaction wheels, star trackers, thermal control, radios, and solar arrays already integrated and tested. No heroic customization, just a short menu of options that bolt on like Lego pieces. Step 2 is the ride. Solar electric propulsion, iron engines driven by sunlight, turns patience into performance. It does not yank you out of the neighborhood. It nudges you steadily until you are flying faster than anything chemical could deliver on short notice. The booster stage can be its own ready-to-fly module, parked in high orbit and checked monthly like a satellite on standby. When the alert arrives, the payload bus mates with the electric stage in orbit. The engines light up and whisper their way to the required speed, while mission planners refine the final aim point with fresh astrometry from the ground. Because time is the tyrant, the mission profile is a recipe with a few interchangeable spices, rather than a chef's tasting menu. If the target is inbound with a friendly geometry, you choose the direct chase, burn early, angle for an intercept arc, and plan to fly through the coma at a safe distance. If the geometry is awkward, you pick the two-step, a quick inner solar loop that steals energy from a close brush near the sun, then a long thrusting leg toward the visitor's outbound trail. Either way, you plan to meet the target on its terms, a moving rendezvous with the sun as the third character in a tightly choreographed dance. Now the payload. A rapid mission carries a practical kit that answers the right questions without trying to write an encyclopedia. Begin with a wide-field camera for navigation and dust environment awareness. Add a narrow-field imager, with a zoomed-in, high dynamic range sensor for nucleus and jet structure. Bring a simple spectrometer that covers visible and near-infrared light to read the main gases and basic minerals. Tuck in a dust analyzer the size of a lunchbox to taste particles during a cautious fly-through. Finally, mount a tiny magnetometer on a short boom to listen for the handshake between the solar wind and the coma. That is it. If it does not help you navigate, keep the craft safe, or answer a first-order science question, it waits for a future mission. Fast planning does not mean reckless planning. You structure the project like a fire drill. Before discovery, you have simulation days in which teams practice receiving an orbit update and building a trajectory within 48 hours. You keep a library of pre-approved flight rules that can be tailored, not invented. You prepare a set of encounter geometries with canned pointing plans. Approach from behind the dust flow if activity is strong. Pass above the sunlit limb if jets are moderate. Swing wide and look back if the nucleus is quiet. Operations rehearsal becomes a sport. The scoreboard is timed to decision with safety margins intact. Communications get the same treatment. A two-piece link strategy keeps the data flowing even when geometry turns ugly. High-gain antennas handle the big downlinks when the craft is steady and the pointing is easy. A rugged, medium-gain antenna handles housekeeping and low-rate science during sloughs, keeping the stream alive when the spacecraft is busy dodging dust or pivoting to find stars. All of it rides on tried and tested radios and codes, chosen for reliability, not novelty. Power is the one place where you allow a little luxury, because it buys resilience. Slightly oversized solar arrays mean you can keep the ion engines nibbling and still run the instruments. A battery with healthy reserves lets you coast through shadowed periods near the sun or brief outages during attitude changes. Heat management is similarly pragmatic. Simple louvers and radiators that shift the thermostat without fancy fluids or risky experiments. Risk posture deserves plain talk. A rapid mission accepts that not every instrument will see perfection. The goal is to secure a floor of guaranteed returns and then stretch for extras if conditions permit. Fly by at a conservative distance first, then spiral in if the dust and gas environment allows. If activity spikes, pull back and lengthen the observation arc. The mission is a marathon of small wins, not a single daring leap. The budget benefits follow naturally. Off-the-shelf hardware and a tight scope keep costs in a column that legislatures can defend in a normal cycle. Shared infrastructure, like the stored electric stage and the standing operations team, amortizes across more than one opportunity. If the first mission misses the perfect corridor, it still demonstrates the concept and leaves you staged for the next visitor. Why is all of this better than simply building a larger, slower, made-to-order flagship? Because the window does not care about our paperwork. An interstellar traveler is a live event with an expiration date. Every month, shaved from development, can buy you tens of thousands of kilometers of better geometry, brighter targets, and cleaner spectra. Every time you choose familiar hardware over bespoke craftsmanship, you trade style for presence. In space exploration, being early beats being fancy. The cosmos rewards the runner, who shows up to the starting line more than the designer still drawing shoes. Set the phone on the wall to loud, stock the shelf, practice the drill. When the next alert pings, we roll. And once we have a craft on the way, we can squeeze even more performance from clever paths. Next chapter, we bend trajectories like origami, gravity assists and close solar swoops that turn modest engines into headline speeds. Chapter 11, Slingshots and Super Maneuvers. If rockets are the legs, trajectories are the dance. And when your legs are short, you learn better moves. Welcome to gravity assists and sun-skimming burns, the parts of orbital mechanics that feel like cosmic parkour. Style points are optional. Getting there faster on less fuel is the real trick. Start with the slingshot, also known as a gravity assist. Picture jogging past a moving walkway at the airport and stepping on at the perfect moment. You did not suddenly grow stronger. You borrowed a little forward push from something already in motion. Planets are those moving walkways. They circle the sun with enormous momentum. If you aim just right and fly behind a planet in its orbit, you leave with more speed relative to the sun. Fly the other way, cut in front, and you donate speed instead, which can be useful when you need to hit the brakes without carrying a mountain of propellant. The planet barely notices the trade. You steal a pinch of momentum from a banquet table. The magic is geometry. A gravity assist is not a tug rope, it is a curve. Your spacecraft falls toward a planet, swings around, and departs on a new heading. During the swing, the planet's gravity changes your direction. Because the planet itself is moving, your new direction translates into a higher or lower speed relative to the sun. Think of it as merging onto a highway, using the slope of a cloverleaf to pick up speed, then leaving the ramp aligned with fast traffic rather than farm roads. You did not floor the pedal. You used the road to do the work. One slingshot is good, a chain is better. With careful timing, you can link assists like stepping stones. A small spacecraft can leave Earth, dip near Venus for a kick inward, then loop past Earth again to harvest speed, and even tip a hat to Mars or Jupiter for a final boost. Each pass is a pencil stroke that redraws your orbit, trading weeks or months of calendar time for speed that would have cost an absurd amount of fuel. This is why the clever missions look like doodles. They are not lost, they are budgeting energy. Now for the wilder move, the sun-skimming burn. The closer you are to a gravity well, the more useful your engine becomes. Fire your thruster where your speed is greatest, and you get the most bang for each precious teaspoon of propellant. Near the sun, you are moving like a stone in a slingshot. If your heat shields can stand the glare, you can dive inward on a tight arc, then light your engine at the bottom of the swoop. That push, delivered at peak speed, stretches your outbound path dramatically. The result is a departure that leaves even big chemical rockets looking winded. This is not a daredevil stunt for its own sake. It is a cold, practical way to turn modest hardware into headliner performance. The ingredients are predictable: a heat shield that refuses to panic, a guidance system that can hold a steady hand while the world outside the window turns white, and a thruster that runs clean and steady when temperatures soar. You do not need to be fancy. You need to be resilient. As a bonus, the closer you get to the sun, the stronger your solar arrays perform. So a solar electric stage can sip photons like an espresso shot right when you want to push hardest. There is a misconception that gravity assists are mysterious. They are not. They are choreography. Aim your approach slightly behind a planet's direction of travel, and you come out with more heliocentric speed. Aim slightly ahead, and you leave slower. Slide over the north or south pole of a planet, and you tilt your orbital plane. A neat trick when you need to climb out of the flat disk where most planets live. With outer giants, you can even mix these moves. Gain speed and tilt in a single pass, like a skateboarder who clears a gap and also rotates mid-air. The catch, of course, is timing. Planets are punctual, but not patient. The alignments that make a good slingshot come and go, miss by a few weeks, and the walkway has already moved on. That is why mission planners keep ephemeris calendars the way surfers keep tide charts. When the window opens, you go, even if your logo is still drying. The reward for punctuality can be life-changing for a mission: a faster arrival, a better angle for lighting, or an approach that avoids dangerous debris. You might ask, why not always slingshot everywhere? Because each assist is a negotiation. You accept extra calendar time, added complexity, and more chances for small errors to multiply. Sometimes, the direct path wins, but when the target is screaming through the inner system on a one-time visit, slingshots and sun skims turn a "we cannot" into a "we might." They pull distant doors within reach of a spacecraft that fits in a small budget and a small fairing. Speaking of doors, clever pathways also offer escape hatches. If your first plan is to meet the visitor inbound, but weather or geometry spoils the view, a backup sequence of assists can aim you at the outbound trail instead. Think of it as two routes to the same concert. City streets, if traffic is kind; ring road, if downtown jams. You might miss the opening act, but you still get the show. For a rapid response mission, The best part of these maneuvers is how they multiply options. With a single electric stage and a heat shield, you can choose between a gentle multi-slingshot for precision or a bold sun dive for raw speed. With a chain of small corrections baked into the plan, you can tweak the path as new measurements refine the target's orbit. Flexibility is not a luxury. It is survival when the quarry is a moving target with a changeable personality. Orbital mechanics asks for patience, but it rewards audacity that respects physics. The universe has built-in ramps. We just have to show up when they line up and keep our balance during the turn. Slingshots let small spacecraft punch above their weight. Sun-skimming burns turn sunlight into leverage. Together, they make the impossible merely difficult and the difficult deliciously tempting. Now that we have the moves to reach a fast visitor, what do we use for boots on the ground, or rather, instruments in the flow? Next chapter, we unfurl sails, beams, and efficient engines, the hardware buffet that makes closing the gap not only feasible but elegant. Chapter 12, Sails, Beams, and Future Engines. Imagine chasing a sports car with a bicycle and discovering the wind itself can push you faster than your legs. That is the idea behind sails in space. Use sunlight or a beam to push a featherlight mirror and let physics do the pedaling. If our quarry is a one-time, no-do-overs interstellar passerby, we want every trick that turns patience into speed. Welcome to the hardware buffet. Solar sails, beamed power sails, and high-efficiency electric engines that sip propellant like it is espresso. Start with solar sails, the purist's favorite. A solar sail is a giant, weight-shy sheet that reflects sunlight. Photons have no rest mass, but they carry momentum, and when they bounce, they nudge the sail. One nudge is tiny. Millions upon millions of nudges, all day, every day, add up. The result is slow, steady push without a single drop of propellant. The art is geometry. Tilt the sail, and you can steer, trading a little push forward for a little push sideways, the way a sailor tacks across a lake. Near the sun, the push is stronger, so small craft can spiral inward to harvest more sunlight, then turn that pressure into a slingshot outward. Solar sailing is patience weaponized. You do not sprint, you accumulate. Sails are not just big sheets. They are origami that must survive being folded inside a rocket, then unfurled into a flawless gleam. Wrinkles steal performance, shadows bite into thrust, and even micrometeoroid pinholes can spider into tears if the material is not right. And again baby these films, the way violin makers baby spruce, ultra-thin metallic coatings, fiber reinforcements, and booms that lock like tape measures give a sail structure without turning it into a manhole cover. The lighter the sail per square meter, the ruder the shove from sunlight, and the ruder the shove, the more useful the craft becomes for a chase. Now crank the idea up, beamed power sails. Instead of sunlight, you feed the sail a concentrated push from Earth or lunar lasers, or from microwave arrays, perched where orbits are friendly. A beam turns night into day on command. You can time the shove, aim it like a spotlight, and pour on power when the geometry is right. The sail itself might be reflective for lasers or tuned for microwaves, and it could carry a tiny chip-sized payload that is all sensor and radio and hardly any mass. A short, fierce beaming campaign can fling a butterfly weight probe onto an intercept path that a conventional rocket would envy. Beamed systems are part hardware, part choreography. You need transmitters with eyes good enough to keep the beam on target across vast distances, plus safety rules so you do not fry someone else's satellite or incidentally set the moon's dust shimmering like a disco ball. If built with care, a beamed sail fleet becomes a strategic asset. Whenever a new visitor is announced, you pull a sail out of its case, wake a handful of stations, and give the probe a push. The beam does the heavy lifting. The probe just holds on. Sails have a cousin in the electric engine family, ion and Hall thrusters, and their bulkier cousin, magnetoplasma dynamic thrusters. These devices throw charged particles out the back at speeds no chemical rocket can touch. Because each particle carries so much energy, You need far fewer to get a big change in velocity. The catch is power. Electric engines thrive on watts. With big solar arrays and frugal instruments, a small spacecraft can thrust for months, even years, building up speed until the trajectory looks like a designer drew it with a fine pen. Electric engines complement sails beautifully. Where a sail gives you free push, but little control near shadows, an electric engine gives you precise kicks regardless of light level, as long as your panels or batteries can feed it. A clever chaser might spiral inward under electric thrust, dip close to the sun to soak up power and speed, then open a sail at perihelion to ride the photon river outward. That blend, electric for the steering, sail for the stamina, turns a small platform into a rangy hunter. Now for the fun speculative combo, a quick launch bus plus a pop-up sail. Picture the rapid response spacecraft we daydreamed about earlier, except its payload bay hides a folded square of brilliant foil. At launch, the bus uses conventional propulsion to reach an efficient staging orbit, or to rendezvous with a stored electric kick stage, while the electric engine is whispering up speed. The craft approaches its planned sunlight sweet spot. Then the sail blooms. From that moment, the engine and the sail work in relay. When panels are drenched in sunlight, the engine runs hot, and the sail tilts to add forward push. When geometry turns awkward, the engine throttles down, and the sail does the work, keeping the craft from wasting momentum. If ground stations happen to field a laser or microwave array, they can top up the push during a narrow window, adding a beam-powered sprint at the perfect moment. This hybrid has serious perks. It keeps mass low, so the bus can be off the pad quickly. It offloads the hardest job, sustained push, onto sunlight, which is always on. It leaves precious propellant for hazard avoidance near the visitor, where a burst of sideways speed might be the difference between a graceful fly-through and sandblasting, and it scales. Send one now and build a copy next year. Reuse the playbook, swap in a different sail material, update the beam schedule. Progress becomes iterative instead of once per generation. What about control? Sails need attitude control that is nimble but stingy. Tiny reaction wheels, vanes on the sail corners, or even shifting the center of mass with a sliding weight can keep the mirror at the right tilt without burning fuel. Electric thrusters need gimbals that can aim without shaking the sail to pieces. These are engineering problems, yes, but they are the kind of problems engineers love. Tuning forks and balance tricks, not magic. The future engine catalog does not end here. There are concepts that breathe the solar wind, scooping charged particles for reaction mass, and others that heat propellant with concentrated sunlight. There are dreams of compact nuclear electric systems that make watts where sunlight is thin. But even without those, sails and electric engines are enough to turn the next intercept from wish to plan. In the end, sails and beams ask us to think like sailors, not sprinters. Read the light, trim the mirror, nudge when it matters. This philosophy pairs perfectly with quick launch kits on the shelf. When the alert pings for the next interstellar passerby, we will not argue about the perfect engine. We will grab a sail, wake the beam, and go. And when we arrive, we will want to taste the coma without planting a foot. Next chapter, we show how to sample a breath safely while staying on the move. Chapter 13, Sample Without Landing. How to taste a coma safely. Imagine driving past a bakery at dawn. You do not go in, you do not order, you just crack the window and inhale. If the wind is right, that one breath can tell you there is cinnamon on the rolls, lemon in the glaze, and a baker who takes their job seriously. Sampling a comet's coma is the space version of that drive-by sniff. We skim the outer envelope where vapor and dust spill outward, collect a few motes and molecules, and then peel away before the oven mitts come flying. Done well, a single pass can rewrite chapters because it lets us touch material that has barely met sunlight. The heart of a safe fly-through is gentle capture. We cannot smash into dust at highway speeds and expect subtle chemistry to survive. Enter aerogel, a pale blue feather-light material that is mostly empty space. Think of it as a cloud that forgot it was supposed to float. When a dust grain hits aerogel, it burrows a tiny carrot-shaped track. The track slows the particles smoothly, spreading the shock over a longer distance, so fragile bits do not shatter into nonsense. Each track is a breadcrumb trail, pointing to a preserved grain that still carries the layers, pores, and trapped volatiles that tell a story about its birth. The collector tray can be a patchwork, tiles of different densities, to catch a range of particle sizes, from powdery flecks to sand-like specks. Dust is only half the flavor. We also want the breath itself, the whisper of gases escaping from the nucleus. That is where the ultraviolet sniffers come in. Sunlight pumps energy into certain molecules, and they glow at very specific colors. Instruments that separate light into a rainbow can count those colors and tell us which gases are present and how fast they are streaming. A fly-through spectrograph acts like a nose that can also measure the temperature and mood. One moment, it is registering water vapor. The next moment, it sees a surge of carbon dioxide or a cameo from rare species that only appear when a fresh vent wakes up. Because the coma changes with sunlight and rotation, this real-time readout matters. We are catching a traveler mid-breath, not a bottled sample from last year. Between the big pieces and the breath lies a world of crumbs, and that is where dust analyzers earn their keep. Some are simple counters that register impacts, telling us how many particles we met and how energetic they were. Others add a tiny oven and a mass spectrometer, baking grains just enough to coax out their volatiles and weigh the fragments of their molecules. A careful heating schedule can tease out what evaporates first and what hangs on until later, which in turn maps to how those grains formed and aged. The point is not to make a lab in space. It is to choose a few tricks that turn a handful of dust into a biography. All of this rides on choreography. The spacecraft must cross the coma at the right distance and the right speed. Too far out and the breath is thin. Too close in and the dust turns rude. Mission planners watch the light curve for hints of rotation, steer to pass through a region likely fed by a steady vent, and time the crossing so the sun lights the scene without blinding the cameras. The craft points the collector into the wind, keeps sensitive optics behind shutters, and flies the profile like a skier slicing through powder, smooth, committed, no sudden lunges. Contamination control is the not-so-glamorous hero of this story. If you hope to claim that a faint whiff is truly from another star's pantry, every part of your spacecraft that touches the sample must be cleaner than a surgeon's hands. Collectors are baked and bagged before launch. Covers stay sealed until seconds before the pass. Surfaces near the instruments use materials that do not shed their own vapors when warmed by sunlight. Even the way the spacecraft sneezes out thruster puffs is choreographed to avoid blowing exhaust across the intake. After the pass, the collector closes like a book and tucks itself away to keep stowaway reactions from continuing in the dark. You might ask, why chase a breath at all when pictures look prettier? Because composition answers questions pictures cannot. The gases in the coma betray which ices sit near the surface and how the layers are organized. A sudden rise in carbon monoxide hints at pockets of ultra-cold material closer to the top than expected. A deficit of nitrogen-bearing compounds might imply a childhood spent where gentle heating drove that ingredient off. Ratios of heavy to light versions of elements act like timestamps and thermometers, telling us how far from a star the material condensed and how it has been processed since. And the dust itself, when captured whole, can reveal delicate organics and microtextures that would vanish in a rough landing. There is another payoff to a quick taste: comparison. If we gather the same kind of data from several visitors, local and interstellar, we can build a library of recipes. Does our traveler carry more of the easy-to-boil ices than homegrown comets at the same distance from the sun? Do its grains show different layering or porosity? Are the heavy-to-light ratios shifted in ways that demand a colder nursery? Patterns across many quick breaths can expose family resemblances and deep differences, sharpening the map of how planetary systems cook. Of course, we respect the risk. Dust can sandblast, vapors can coat optics, and a single surprise jet could push the vehicle into a posture it does not love. That is why we carry sacrificial shields up front, park critical sensors behind flick-open lids, and keep a gentle sideways thruster in reserve to slide out if the particle counter starts clicking like a popcorn machine. The watchword is prudence. Get enough signal to answer the big questions, then leave with your prize intact. In a way, a fly-through is the purest form of encounter. We are not trying to conquer the surface or plant a flag. We are passing through a living exhale and letting it paint our instruments for a heartbeat. That heartbeat can hold the first sighting of a delicate molecule, the cleanest sample of uncrusted dust, or an isotope ratio that shifts the origin story by whole orbits of distance. One breath, one pass, one chapter, rewritten. Next, we widen the lens from instruments to infrastructure. How the resources aboard a comet, ice for propellant, mass for shielding, could someday fuel and protect long voyages, turning a passing freezer into a traveling gas station. Chapter 14. Resources on the road, fuel, shielding, and life support. Picture a deep space crew pulling up beside a dark, icy body and looking at it not as a mystery, but as a supply depot with bad lighting. The promise is simple. If you can melt it, move it, and store it, you can fly farther and safer. In space, your gas station is whatever you can turn into steam. Start with fuel the easy way, hot water. A small lander touches down and snakes a warm probe into the crust, the way you slide a metal straw into a stubborn smoothie. Heat does the heavy lifting. Ice softens, melts, and wicks into a collection bag. No drill drama, no fireworks, just patient thawing. Pump that melt into a tank, heat it, and push it through a nozzle. Steam rockets do not win beauty contests, but they are brutally honest. They drink from the same ice they scoop, and the exhaust is water that will not gum up your neighborhood. For cargo tugs or short hops around a comet, steam is the space equivalent of burning logs in a potbelly stove. Low-tech, reliable, and ready whenever the kettle boils. If you want more punch, split the water. Electrolysis takes electricity and turns liquid into oxygen and hydrogen. Store both, and you have clean propellants for engines that run hot and efficient. The process is as cozy as a kitchen gadget. A stack of plates, a trickle of current, bubbles rising into separate domes. The hard part is not the how, it is the where. Tanks need to stay cold and calm. That means sunshades, reflective blankets, and a shadowed nook so boil-off does not steal your hard-won stash. Think of it as packing ice cream for a summer road trip. Keep it shaded, keep it sealed, and do not park under a heat lamp. Power is the rhythm section behind all of this. A comet visit offers two natural sources. Close to the sun, solar arrays work overtime, happy to feed heaters and pumps. Farther out, you slow down and lean on compact generators that sip nuclear heat. Either way, you want steady watts rather than sudden gusts, because melting, filtering, and splitting are patient crafts. A nice side effect: waste heat from your power system can feed the thaw. No jewel should leave without doing a chore. Raw meltwater is not perfect. It may carry dust and dissolved gases that you do not want in valves and membranes. The fix is a simple filter train. Let the heavy grit settle, push the rest through cloth, then through a fine mesh, and finally through cartridges that trap bite-sized impurities. What emerges is clean enough for plumbing and friendly to electrolyzers. For crew life support, give it one more pass through the purifier, and you have drinkable supplies without waiting for a tanker from home. Shielding is the second big prize. Space is sprinkled with radiation you would rather not meet unprepared. Water is a champion at soaking it up. Stack tanks around the crew cabin like a protective moat, and you have a wall that pulls double duty. One part armor, one part pantry. As you burn through propellant on the trip, you reshuffle storage so the remaining mass stays between the crew and the harsh side of the sky. If you happen to land, you can pile bags of wet regolith and ice blocks around a habitat the way you stack sandbags before a storm. No exotic alloys, just mass in the right place. Life support thrives on the same pipeline. Melt gives you drinking water, washing water, and a base stock for oxygen. Electrolyzers feed tanks and lungs alike. Pair them with simple scrubbers that capture carbon dioxide from cabin air, and you have a loop that keeps the atmosphere fresh with only small top-ups from the local well. You can even run fuel cells in reverse during a power lull, recombining oxygen and hydrogen to make electricity and fresh water in a neat 2-for-1. How do you run this station without turning the comet into a snowblower? Gently and tidily. Wrap the worksite in a translucent bubble or curtain to catch drifting frost and dust. Vent waste vapor through a pipe that points away from your landing gear and instruments. Anchor your hardware with screws and harpoons set at a shallow angle so they grip without splitting fragile crust. And always keep a grip line to your lander, because this is a playground with almost no gravity. One careless shove and your pump cart becomes a satellite. Logistics matter as much as chemistry. You do not want to refit a spacecraft in a blizzard, so the gear should be modular and glove-friendly. Hoses with quick couplers, tanks that click into racks, a maintenance kit no bigger than a toolbox, with spare seals, filter cartridges, and a heater wand that can thaw a stubborn valve. Telemetry should tell you, at a glance, where every kilogram sits. What is liquid? What is gas? What is cold? What is cozy? No guesswork, no surprises. Safety is a mindset. Warm slowly so you do not pop a cavity wall and trigger a vent under your feet. Keep a backup line from your power source to your heaters so a single fault does not freeze the works. Never point a thruster at the supply you just collected. And keep the most precious tank crew water physically separate from propellant bays so you do not need to choose between drinking and maneuvering if a seal misbehaves. Will every icy body cooperate? No. Some are powdery and leak like a colander. Some are rock hard and need more patience. That is why scouting comes first. A pass with radar to guess at layering, a sniff for meek outgassing that marks warm pockets, and a few test melts on small patches to check how the material flows. Once you find a friendly vein, you set up shop for as long as sunlight and schedules allow. The reward is independence. Instead of hauling every kilogram from Earth, you top up along the way. You turn a cold lump into propellant, padding, oxygen, and drinking water, and then you leave it tidier than you found it. With that confidence, the map of reachable missions gets larger and kinder. Next, we look up from tanks and hoses to the celestial map itself. Tracking a fast stranger teaches navigation tricks that will guide us between stars. Chapter 15 is all about how a galactic drifter sharpens our sense of direction. Chapter 15, Navigation Lessons from a Galactic Drifter. Imagine trying to photograph a dragonfly while riding a roller coaster, using a camera you assembled on the way up the hill. That is navigation with a fast interstellar visitor. The prize is not only a successful flyby now, but a better playbook for hopping from star to star later. Every update, every correction burn, every so it drifted a little left, goes into a manual that future crews will thank us for. It is the universe's way of saying update your maps. Start with ephemerides, the celestial equivalent of a friend's location pin that actually means something. At first, the pin for a new visitor wobbles. Early measurements are sparse, the angle is lousy, and the object is faint. But a global ballet of observations, spaced in longitude, latitude, and wavelength, turns wobble into certainty. Each night's position narrows the where could it be tomorrow oval. Throw in parallax from widely separated observatories, and depth stops being a guess. This cadence teaches a key habit for interstellar navigation. Do not wait for perfect data. Iterate quickly with good data. Fast loops beat slow perfection, because your target is not waiting. Then we learn to model the mischief. A visitor's path is not a simple gravity-only curve. Outgassing can add a whisper of thrust. That tiny push, integrated for weeks, becomes a meaningful nudge. The lesson is portable. When you sail between stars, your own micro-forces, thermal recoil from warm panels, faint leaks, even uneven radiation pressure. By fitting small non-gravitational accelerations to the trajectory, we sharpen our sense of how petting a cat in the wrong direction can move a spacecraft over time. The takeaway is to carry navigation models that expect tiny gremlins, measure them, and fold them into course corrections rather than pretending the universe is tidy. Clever targeting is the next chapter of the playbook. You rarely aim at where the object is. You aim at where it will be when you and light and dust all line up in your favor. That means choosing encounter points not just for closeness, but for lighting, background star fields, and safety. Sometimes the best, closest approach is not the literal closest. A slight offset gives you sunlit terrain for images, a cleaner look through thinner coma, or a geometry that makes occultations possible. The habit we build here, trade a little distance for a lot of quality, will help when threading past exoplanets, where a better angle can beat a tighter pass. We also practice statistical targeting. Early in a campaign, the error ellipse on an encounter point can be big enough to hide a small country. Instead of betting the mission on a narrow thread, you design a corridor, a family of paths that all yield good science, with small tweaked burns available as you get better numbers. It feels like bowling with the gutters raised, but it is really resilience in action. For interstellar voyages where signals crawl and windows are rare, resilient corridors are the difference between heroic lore and awkward silence. Tracking a drifter trains our eyes too. Optical navigation is an art that blends star tracker calm with quick reflexes. Against a field of stars, the target is not just a point, it is a point that moves exactly as predicted, if your model is right. Deviations of a hair's breadth tell you when to trim. We discover which backgrounds confuse our senses, how to adjust exposure when dust brightens the sky, and when to switch from star field matches to limb tracking or optical flow on the target's own features. That mix and match approach, use stars when you can, use the target when you must, will be essential when cruising through unfamiliar skies, where catalogs are thinner and surprises are thicker. Radio also gets a workout. Doppler and ranging sessions teach us how to extract exquisite velocity and distance from signals that whisper. We learn to schedule passes to catch the most informative parts of the trajectory, and we learn to trust onboard autonomy during long gaps. That rhythm hints at a future where deep space craft will carry their own mini ground stations in logic, a navigation brain that predicts, observes, updates, and decides without asking permission every hour. Autonomy, in fact, is the quiet hero of a drifter chase. Onboard software can treat navigation like a living thing, watch, compare, predict, act when the coma brightens and star trackers lose their nerve. Autonomy switches to a fallback visual mode. When dust fries a planned line of sight, autonomy slews to an alternate star field and keeps the solution alive. When the target's non-gravitational push makes the next correction burn time sensitive, autonomy fires a tiny trim, now rather than a big fix later. This mindset, small frequent nudges over rare grand gestures, slims risk and saves propellant, a lesson tailor-made for star-by-star flights. We also pick up street smarts about windows. Occultations, for example, are navigation candy, predicting that blink as the drifter crosses a distant star, teaches us to propagate uncertainties forward, map them onto Earth, and position telescopes along a thin path in real time. The same math, scaled up, lets future missions thread their way through exoplanet systems to catch transits, glints, or atmospheric backlights on the fly. It is choreography learned in miniature. Another habit that sticks, keeping a living covariance. That is a fancy way of saying we carry not just where we think the object is, but how confident we are in each direction. and we update that confidence every time new photons arrive. Command teams who see uncertainty as a map layer make smarter choices about when to burn and when to wait. Crews who travel between stars will need that intuition like oxygen. Patience in the right hour is as valuable as thrust. Finally, a galactic drifter trains our humility. We relearn that maps are stories we tell about measurements, and stories get better with edits. We practice admitting the model is off, rolling in the new term, and moving on without drama. That habit will matter when the first interstellar cruise meets a dust lane harsher than expected, or a magnetic pocket that behaves like a funhouse mirror. In short, chasing a fast stranger turns navigation from a static craft into a living dialogue. We iterate faster, model finer, target smarter, and let autonomy earn its wings. With those lessons banked, we can face the next chapter's human side. How to balance public thrill with scientific caution when rumors start sprinting faster than facts. Up next, culture shock. Public hype versus careful science. Chapter 16. Culture shock. Public hype versus careful science. Careful science. There is a rhythm to cosmic news. First comes the spark. A faint dot moves in a way that makes astronomers lean forward. Then comes the shout. Headlines promise everything from alien artifacts to doomsday pebbles. Social feeds go full drumline. In the middle of that noise, the scientific method clears its throat, rolls up its sleeves, and starts asking small, slightly boring questions that turn out to matter. Black holes delete browsing history permanently. Scientists delete bad hypotheses. More politely, calm questions are not a buzzkill. They are a compass. When a sensational claim surfaces, say the object must be artificial because its brightness flickers oddly, the response is not a rebuttal shaped like a meme. It is a checklist. Could the flicker come from a lumpy, tumbling shape? Did the camera saturate on a few frames? Do other telescopes see the same rhythm? Is there a mundane way dust jets could imitate the pattern? Each question narrows the playground where wild ideas can run. If the answers survive that gauntlet, then we earn the right to be excited. If they do not, we earn the right to move on. Extraordinary ideas earn their stripes through prediction, not charisma. A flashy narrative that explains yesterday is entertainment. A good hypothesis sticks its neck out about tomorrow. If someone argues our visitor must be made of an exotic alloy because of its light curve, the sober reply is, great, then we should see a specific color signature next week when viewing geometry improves. If instead we see the telltale glow of simple gases, the exotic story shrinks. That is not defeat, that is progress. Ruling out feels less heroic than announcing a discovery, but the history of science is paved with quiet victories where a disciplined nope saved everyone from chasing mirages. Another friction point is speed. News cycles sprint, data plods. Observations arrive in weather windows, across time zones, with gaps for dawn and bureaucracy. A careful team will show their work with uncertainties attached, like parentheses around every claim. Hype tends to toss the parentheses because caveats do not share well. The cure is not to muzzle enthusiasm. It is to teach audiences that uncertainty is not weakness. Those shrinking error bars are the story. We are getting closer, not lost. Language can help or harm. Words like unprecedented and never seen do heavy lifting online, but they often mean we have not seen it often, or we have not seen it this bright. Scientists try to choose verbs with talk, consistent with, intention with, ruled out at this level. These may sound dry until you realize they are levers that move mountains. Consistent with keeps multiple doors open while we gather more light. Intention with invites skepticism without slamming hope. Ruled out honors the time we will not waste tomorrow. A classic hype trap is the single spectacular figure. One outlying point on a chart becomes a talisman. Careful science answers with replication. Can we get the same behavior with another instrument, from another location, at a different time of day? If the signal survives travel, lighting changes, and new hardware, it graduates from rumor to result. If it fades, we just learn something equally valuable. Our measurement was sensitive to a hidden confounder. The internet rarely cheers for that lesson, but future missions will. There is also the tug of narrative bias. We love a tidy arc. Mysterious visitor upends theory. Reality prefers messy growth. Mysterious visitor nudges theory, which absorbs the nudge and becomes a little more true. That is satisfying in a different way, like watching a craftsman plane a board until the surface gleams. When public hype demands a plot twist in every act, careful science counters with patience, explaining that the twist is cumulative. Each observation is a small hinge. Many hinges rebuild a door. Skepticism is not cynicism. True skepticism asks for evidence and keeps listening. Cynicism stops listening. When a claim arrives from outside the usual channels, an independent observer, a small team with a bold idea, skepticism gives it a fair hearing, but demands receipts, data access, processing steps, uncertainties, clear predictions. If the receipts show up, welcome aboard. If they do not, the responsible choice is to set the claim aside without character assassination. The goal is a culture where being wrong costs little, but hiding methods costs a lot. Why does ruling things out deserve applause? Because elimination sharpens tools. When we discover that a brightness flicker is camera chatter, our pipelines get better at catching chatter. When we find that a supposed anomaly is just sunlight scattering off a peculiar dust grain size, models upgrade. The next time, we reach the truth faster. Quiet corrections are compound interest for future discovery. There is also a social contract at stake. Public trust in space science thrives when we are transparent about uncertainty and swift to correct ourselves. That means publishing data when possible, explaining when it is not, and avoiding the temptation to speak beyond what the photons support. It also means giving credit widely. Professional observatories, citizen scientists, mission teams, students pulling late nights with coffee and stubborn code. Hype loves a lone genius. Reality is a chorus. So how should audiences ride the wave? Enjoy the wonder, bookmark the bold threads, and then check back when the light curve has doubled and the spectra have piled up. Ask what changed between headline number 1 and headline number 2. Look for the predictions that came true or did not. Celebrate the we learned that it is not X, because that is the scaffolding under every we found Y. In the end, hype and care do not have to be enemies. Curiosity lights the fire. Discipline keeps the lab from burning down. We can be thrilled without being credulous, cautious without being dull. The cosmos is generous with surprises. We just have to meet them with clear eyes and patient hands. Next, we swap headlines for headwinds, the invisible climate between stars that every traveler must cross. Chapter 17 delivers our interstellar weather report. Radiation, dust, and magnetic fields, and what a single flyby can teach us about that vast, unseen sea. Chapter 17, the Interstellar Weather Report. If the solar system is a cozy backyard with a bright porch light, the space between stars is the long, dark street beyond the fence. No air, no clouds, just a sea of high-energy particles, whisper-thin dust, and magnetic fields that curl and twist like invisible rivers. We do not get many chances to stick a hand out and feel that wind, but every time an interstellar object swoops through, it becomes a moving weather balloon. 3IATLAS is not only a spectacle, it is a postcard from the galactic highway. Let us start with radiation, the background hiss of space. Between stars, charged particles zip along with attitudes. Some were born in shockwaves around dying stars. Others were flung outward by flares from distant suns. Closer to home, our sun pumps out a steady breath that forms a bubble around the planets, pushing back the deeper river. When a traveler from beyond crosses that boundary, it carries the marks of both worlds. The coma, its thin atmosphere of gas and dust, meets the solar wind and begins to glow in faint, ghostly colors. That glow tells us how strong the wind is today, and how the deeper, older radiation has weathered the surface over eons. A crust that is brittle and dark may have been sandblasted by galactic particles for ages. A fresher look could mean the object was shielded inside a dense nursery before it was kicked free. Now picture dust, the stubborn confetti of the Milky Way. It is not the soft fluff under your couch. It is tiny glassy grains and carbon-rich specks, far fewer than a whisper per room, but important over long distances. Dust dims and reddens starlight, but it also leaves fingerprints on travelers. As 3I/Atlas cuts through sunlight, its tail reveals how grains of different sizes respond to the gentle push of light and the tug of the solar wind. By comparing the grain sizes we infer near our sun with the likely grain sizes it wore in the dark, deduced from how easily activity starts, we get a before and after picture. Think of it as checking the treads on a well-traveled tire. The pattern of wear hints at the road it came from. Magnetic fields are the third player, and they are trickier. You cannot see them, but you can watch what they do. The solar wind drags the sun's field lines outward like taffy, and the interstellar medium has its own slow, large-scale field running through it. Where these meet, boundaries form. A passing object turns those boundaries into visible shapes. The comet's coma acts like a windsock, and changes in its direction and brightness map the invisible flow. If the field is strong in a patch, charged particles curve and pile up. If it is weak, they race through. By tracking flickers and kinks in the tail, we can sketch the texture of magnetism near us and learn how that texture might differ from the wider galactic average. You might ask, why does a single flyby help with a report about the vast in-between? Because the interstellar medium is not uniform. It is more like a patchwork of warm and cool clouds, gentle breezes and stiff gusts, quiet lanes and knotty eddies. Our sun is currently drifting through a local bubble of thin, hot gas with pockets of cooler material. An interstellar visitor samples that soup on the way in and brings us a moving experiment. The way its coma forms, the way its tail bends, and the energies at which new emissions appear all serve as thermometers and windsocks. One object gives a line of data. Several objects over time can draw a map. Radiation also leaves deeper clues in the object itself. High-energy particles chip at surface molecules, darkening and hardening the outer skin. They can split complex organics into smaller fragments, then encourage those fragments to rejoin in stranger ways. When sunlight warms the surface during the flyby, the gases that escape carry a memory of that long, slow cooking. By reading which gases come off early and which stay stubborn, we can estimate how thick the weathered crust is and guess how fierce the interstellar rain was. Where it spent most of its life, it is archaeology. By aroma, dust, for its part, tells us about collisions in the between. If the visitor's grains are unusually fine, it may have been sanded down in a region thick with micro-impacts. If larger crumbs survive and loft easily, the space it crossed might have been emptier, with fewer tiny hammer blows. Even the presence of fragile, fluffy aggregates, little snowball clumps, would hint at a quieter road. The tail becomes a diary, not just what is happening now under sunlight, but what has been happening for a very long time in the dark. Magnetic clues grow sharper when we time our measurements against the visitor's rotation. As different active patches turn into the light, jets act like timed puffs into a wind tunnel. The response, how the ionized part of the coma bends and how quickly it rebounds, reveals the stiffness of the field and the density of the charged gas. String enough puffs together, and you can measure the local space weather forecast, the way sailors read gusts on a lake. There is a practical side to this report. Future interstellar craft will cross the same kinds of regions that shaped 3I/Atlas. Knowing where radiation runs high tells us how thick a shield to carry and when to hide behind water tanks. Knowing typical dust sizes and densities tells us how tough to make front-facing surfaces and how often to expect pings on the hull. Knowing the scale and strength of magnetic fields tells us how to tune communication and navigation. Since charged particles and bent fields can play tricks with signals, a single visitor becomes a rehearsal for voyages we have not launched yet. The poetry is not lost on anyone. A stray body from another star system arrives, and in watching it breathe and shed and glow, we learn about an ocean we can barely sense. It is like reading the wind by watching a gull's wingtip. The bird does not know it is a scientist, but its motion writes equations in the air. Next, we step back and look at the larger meaning. Beyond weather and mechanics, what does this visitor change about our plans and our priorities? Chapter 18 ties the threads: why a single flyby can set a new schedule for exploration, and how to be ready when the next postcard shows up. Chapter 18, the big picture: why this visitor changes our plans. If our story so far has been a series of close-ups, path, chemistry, teamwork, daring maneuvers, this is the pullback to a wide shot. 3I/Atlas is not just a one-time spectacle, it is a schedule setter. It is the universe leaning over the railing and saying, "You have had your rehearsal. Now build the show." The practical translation is simple: a ready-to-launch interceptor on the shelf, shared data pipelines that move at the speed of curiosity, and a standing playbook that turns surprise guests into scientific triumphs. Earth may be a rock that won the cosmic lottery, but luck favors the prepared astronomer. First, the interceptor. We need a small, tough spacecraft that can leave during the same decade we learn of the next visitor. Not an art piece, a tool. Standard bus, tested thrusters, a handful of instruments that answer first-order questions, and a heat shield that is allergic to drama. It waits in clean storage with its paperwork done and its anxiety low. When the alert comes, we do not design. We integrate, fuel, and roll. Think of it as a fire engine for the sky. You do not assemble a ladder truck while the siren is wailing. Second, the pipeline. Discovery should flow into analysis without friction. That means nightly positions from survey telescopes, automatic uncertainty updates, and dashboards that any qualified team can query. It also means spectroscopic snippets, dust counts, and brightness curves pushed to a shared commons, where attribution is built in and credit is not a tug-of-war. If a small observatory in Chile catches a sudden flare, a team in Japan should see it with their morning coffee, and a space instrument should pivot before the excitement cools. Knowledge wants low latency, so does opportunity. Third, the playbook. We have learned that the right move depends on lighting, angle, and temperament. Write that wisdom down now. Prepare standard encounter geometries for hot, moderate, and quiet targets. Pre-bake pointing scripts for the obvious passes: over the sunlit limb, down the dust cone, crosswind through the coma, embed go and no-go checklists that can be cleared in minutes, not days. Run drills so nobody asks where the cables are when it is time to move. The goal is not to guess the future. It is to make sure the first hours after discovery are muscle memory. Funding follows form. This is not a once-per-generation flag-planting campaign. It is a standing capability with a modest, steady budget. You would not shutter a weather service between storms. Likewise, keep a small core team employed to maintain the interceptor, exercise the pipeline, and rehearse the plan. When a real target arrives, they will be ready. When the sky is quiet, they will sharpen the tools and train the next crew. Policy matters too. Fast-moving opportunities often die on slow-moving desks. Establish pre-approved, time-critical access to major facilities: space telescopes, deep space antennas, solar sentinels, triggered by objective criteria rather than charm. Build agreements that let national agencies, universities, and private observatories share data quickly without spending weeks negotiating over commas. In the calm before the next visitor, settle the paperwork that steals days when days are the coin of the realm. Do not forget, citizens. Skilled amateurs can extend light curves, snag occultations, and catch weather windows the big facilities miss. Give them clear observing recipes, simple calibration steps, and a route to contribute that is both rigorous and welcoming. When a backyard telescope catches the only clear view on a cloudy week, science wins and the public feels the mission in their bones. Curiosity scales beautifully when you hand it a checklist. The same goes for classrooms, turning a live interstellar chase into lesson plans. Predict the path, compare last night's image, debate the best instrument choice, give students a seat in the control room without leaving homeroom. Today's audience becomes tomorrow's pit crew. And frankly, a generation that can pass uncertainty plots will handle the rest of the century just fine. What does preparedness buy us besides pride? It buys firsts. The first clean sniff of never-warmed ices. The first high-fidelity map of a surface that formed in another nursery. The first direct comparison between a stranger's dust and our own. The first time we watch a magnetic handshake between the solar wind and a truly foreign atmosphere in real time. None of those require a flagship mission. They require showing up on time with the right kit and a plan that wastes nothing. Preparedness also buys resilience. If the next visitor is faint, we already know which filters to stack and which exposures to shorten. If it is rowdy, we know how to route a safe fly-through. If it plays shy near the sun, we know which space-borne eyes can stare past the glare. If it splits, we have play pages for chemistry now. Fragments tonight, dynamics tomorrow. Calm competence beats improvisation when the sky turns interesting. Zoom out even further, and a philosophical payoff appears. A ready interceptor, a live pipeline, a practice team that is not just comet chasing. It is a template for agile exploration. The same machinery can pounce on a newly active volcano world, a sudden plume on an icy moon, or an odd dimming around a distant star. The habit of acting while the universe is talking will rewrite our calendar in the best way. So here is the to-do list taped above the console. Keep a spacecraft warmed and waiting. Keep the data flowing fast and fair. Keep the playbook sharp. Keep the public inside the circle. Do these, and the next starborn traveler will not fly by empty-handed. It will leave fingerprints on our detectors, stories in our spectra, and upgrades in our craft. We end where we began, under a quiet sky that does not stay quiet for long. When the next alert pings, we will be ready to trade surprise for understanding. Earth may be a rock that won the cosmic lottery, but luck favors the prepared astronomer.